Hello everyone, I'm Jianchun from Shandong University. It's my honor to share my work with you. The title of my paper is Aligning and Dynamic Reconfiguration for Resilience Enhancement of Active Distribution Systems. I will present my paper from the following 5 parts. The first part is introduction. The figure 1 is power outage causes for 140 worldwide outage data from 1965 to 2012. It can be seen that natural disasters already account for about 30% of power outages. Considering the global climate changes in recent years, increasing frequent extreme weather disasters occur worldwide. It will result in large-scale power outages and bring serious economic losses and social impact. Located at the end of power systems, distribution systems are the key to directly supply power to customers. So the normal operation of distribution systems in extreme weather is very important to maintain the development of society and economy. In this condition, resilience of distribution systems is introduced to reflect their ability to resist extreme weather disasters, to reduce fault losses, and to restore the original state as soon as possible after the fault occurs. In order to improve the resilience of distribution systems, it is necessary to implement a strategy to restore loads from faults. At present, the researches on the resilience improvement measures of distribution systems mainly include 2 categories. The first type is overhead line cable and replacement of more hardened lines. But the investment for infrastructure hardening is high, that limits its application to large-scale distribution systems. The second type is along digits and reconfiguration. However, merely partial loads can be restored. In this paper, a multi-stage switch strategy based on dynamic programming considering both aligning and fault reconfiguration is proposed to maximize the power supply after faults. The second part is a typical fault scenario, Generation, and Typhoon. The wind speed taking Typhoon as typical extreme weather. The impact of Typhoon on the fragility of distribution system components is analyzed. Bat model is used to simulate the wind speed and direction within the influence area of Typhoon. The wind speed is related to its distance from the line to the Typhoon center, and the wind direction at the point is the tangent direction of counterclockwise. The strong wind force causes the tension on the cross-section of weir and the bending moment on the cross-section of pole. The tensile strength of the weir and the bending strength of the pole are known to normally distributed. Only all the weirs and poles on the line don't break down. The distribution line will operate normally, which can be described as a series model. The typical fault scenarios are screened according to the system information entropy. If the entropy of a failure scenario is too small or too big, reflecting that the probability of this scenario occurring is extremely low, this failure scenario can be considered atypical. Typical fault scenarios with high probabilities of occurrence and serious consequences can be screened based on the formula. The third part is aligning and reconfiguration based on dynamic programming for resilience enhancement. When a typhoon passes, the lines in a distribution system may encounter faults, and thus the power supply gradually falls to the lowest level. Thereafter, the distribution system maintains the minimum level power supply after the first until the typhoon has passed. After the typhoon's passage, the operators carry out emergency repair for the damaged components. The distribution systems will gradually recover from outages and the loads will gradually rise to the normal operating level. The percentage of guaranteed load supply is taken as the resilience assessment index. When faults occur, tie switches and segment switches both adjust their states to change their system topology. By closing tie switches, some OTG areas can be connected to the main network and thus recover the power supply through reconfiguration. By opening the segment switches, islanding can be formed to supply loads in the islands. Considering the capacity limitation of the gas turbine and the limited power transmission capacities, the optimal load shedding is performed in this paper to ensure the maximum load supply. The objective of the optimal load shedding is to minimize the equivalent electricity loss during a typhoon passage, considering the different criticality of loads. The constraints include power constraints on nodes, gas turbine efficiency constraints, shedding load constraints, node voltage constraints, gas turbine air intake constraints, and line capacity constraints. According to the decision of the islanding and reconfiguration, there are a series of different strategies at each time step. At each time step, according to the decision of the islanding and reconfiguration, the chosen tie switches are closed and segment switches are opened for islanding to supply loads in the OTG areas. The selection of optimal dynamic switch strategy is to make a trade-off between minimizing the total load loss caused by the faults and reducing the cost of switch operations, considering the power supply reliability and the economy. The first part is a case study. The proposed method has been tested on a modified IEEE 36 bus distribution system. It is assumed that the landing location of the typhoon is minus 150 kilometers, minus 120 kilometers. The speed of the typhoon is 20 kilometers per hour, and the angle between the moving direction and the positive direction of the opposite coordinate is 45 degrees. Take line 16 as an example. The figure 6 is time varying fault rate curves of the line 16, and the figure 7 is entropy probabilities distribution. It can be seen that the system information entropy is centrally distributed in 20 to 60. And the figure 8 is the probability distribution of fault lines number. It can be seen that the typical number of fault lines is 4 to 9. Hence, taking the 5-foot fault as an example, a typical fault scenario meeting the requirements of information entropy is selected. In this condition, lines 30, 22, 6, 15, and 7 broke down at the following moments. The load curves for normal operation and for the fault scenario with and without resilience enhancement by load shedding model are demonstrated in figure 9, and the result for resilience assessment is displayed in table 1. It can be seen that the resilience of the distribution system is improved significantly by 52.33%. Hence, the distribution system resilience can be enhanced effectively through the proposed aligning and dynamic reconfiguration. The last part is conclusion. Firstly, the failure rate of distribution system is generated by combining typhoon modeling and vulnerability analysis, and the typical fault scenarios are screened based on the system information entropy. Secondly, a dynamic switch strategy considering both aligning and fault reconfiguration is proposed to enhance the resilience of distribution systems. Thirdly, simulation results prove the effectiveness of the method proposed in this paper. Thanks for your attention. I'd like to answer the questions if there are.
Thank you, Jianchun. To keep the time perfectly, So we can open the discussion about this paper. We have some minutes of questions. I don't see any questions in the Q&A section. I have some questions just to open the discussion if you want. One point is, I can start with the questions. In particular, I see that you use an objective function that is a combination between the minimization of the number of switching operation and the maximization of the resilience indicator. I ask if you also tried to put the number of switching maneuvers as a constraint and keeping only the resilience indicator in the objective function. So how this simulation change. So putting as a constraint the maximum number of switching maneuvers that the DSO is willing to operate in these cases. Or so, did you understand the question?
Can you speak slowly? Sorry.
I repeat the question. So I see that in your optimization problem, the objective function is a combination between a resilience indicator and the number of maneuvers, of switching operations. I only wonder if you tried to put the number of switching operation as a constraint and not in the objective function. Because when you have an objective function also a weight, you have to decide what is, how to tune this weight. And so an objective function with inside a weight also give an arbitrary, you have to decide a proper parameter. Instead, if you put the maximum number of switching operation in the optimization problem, then in the objective function, you remain with only one objective, that is the resilience in metric. So I only wonder if you tried to put the number of switching as a constraint, and in case not, how did you choose the parameter alpha to weight the two objectives inside the objective function? Did you understand?
Thank you for your question.
Okay.
In the formula, I think the total load loss reducing the cost of switch operations and the minimizing the total load loss is equivalent. So I think A and B is the same. So the A is 0.5 and the B is 0.5.
Yes, and how did you choose 0.5 instead of 0.3? According to indication of the DSO, or how did you choose this weight?
Because I think the minimizing the total load loss and the cost of switch operations is the same.
Okay.
That's all.
Right. Thank you. And about, is there any question from the audience? I don't see any question. Okay, there is a first question in the question and answer from Lynn Roland. How did you decide on the switching strategies that you use to determine the load shed? So the question is about how did you decide on the switching strategies that you use to determine the load shed?
Thank you for your question. A dynamic switch strategy is proposed, and the optimal dynamic switch strategy with the goal of ensuring the minimum the total power shortage and reducing the cost of switch operations is determined in dynamic switching strategies based on the load law after load shedding. The required loss load ratio is calculated to determine the optimal dynamic switch strategy. That's all.
Okay. I have another question about so there is a following about this question. So you use an optimization problem to determine the switching strategy, or it is done by hand? Can you see the question and answer session? So you can also read by yourself the question if you like it.
Yes, I use an optimization problem to determine the switching strategy. The multi-stage decision-making problem can be divided into several interrelated stages. For each stage, a set of decisions that can be selected. The decision of each stage is integrated to form a decision sequence called a strategy. There are a series of different strategies corresponding to the whole process due to the different selection decisions in each stage. What is more, the decision at the previous moment will affect the decision of the later one. Therefore, the optimal switch strategy for the whole process should be selected from the dynamic switch strategy. That's all.
So we can see that we can say that we have used an optimization problem to determine the switching strategy, right?
Yes.
Okay. Thank you for the question, for the answers and the questions from the audience. I have to go through.